So VSEPR stands for valence shell electron
Pair.
repulsion. Okay, it's a big word. It just really is showing you the shape of the models of the molecules. That's all it does. And so VSEPR is based off of electron domains. So if you remember electron domains, if we look at a central atom, it can have lone pair electrons or it can have bonded pair electrons. And each of them counts as a domain. So we would say this lone pair is a domain. Bonded pair, domain, bonded pair, domain, and a bonded pair, domain. And all those domains take up space. And that's why you would never have like N with H, 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 H all right next to each other. I'm not going to draw all the H's on. But you would never have that because these electrons, because of Coulombic law or Coulombic attraction, they're negative, they're negative, they're negative, they're negative, and they repel each other. They just push each other apart from each other. And so they're going to always spread out as far as they can. And that's how we get the shape of a molecule. So these domains determine the shape of every molecule. We look at carbon. How many domains does it have? Well, double bonds still count as one domain. So one domain, two domains. Does it have any lone pair?
No.
No.
So just two domains. Here's O3. And I don't know if it's O3 or O3 minus, but looking at the central atom, it has one domain,
1,
Two
2,
and three.
3.
two domains. Okay. These aren't drawn necessarily accurately because these would push down and spread out away from these. So this pair would push these down this way, and this pair would push these down that way. And so we end up getting shapes of molecules based off of the domains. And so we'll review them and make sure that you remember them, and then we'll expand upon that a little bit. So with the octet rule, we always ever drew things, the most bonds we ever gave anything was 4 bonds. It had a triple bond and a single, or carbon had 4 singles, or whatever. And so we never had more than 4 domains. But as you were doing Lewis dots and you did things like PCl5, we saw that anything that's in the 3rd row or beyond can have more than 4 domains. It can have more than 8 valence electrons around it because those valence electrons go into the D subshell. And so you can have 5 and 6 domains. And that then opens up all new shapes that we haven't looked at before. So let's review our basic ones here. So linear, the first shape. Linear is always going to give you a 180-degree angle. So BeCl2. Remember beryllium's one of those exceptions. Beryllium's makes 2 bonds, and boron makes 3 bonds. Okay, so those are, again, exceptions. So it's fine with only 4 valence electrons. It doesn't need lone pair. And again, it's an exception. And so as a result, it has a straight line, which we call linear. Linear bond angle is 180 degrees. You must know bond angles for your basic 4-domain shapes. And I'll go over those with you today. Another example of linear would be CO2. It has 2 domains, 1 domain, 2 domain. And so the farthest way that they can be apart from each other is these electrons on one side, those electrons on the other. And so again, we get a 180-degree bond angle. And again, it's always about just the electrons maximizing their distance apart from each other. Being on one side and on the other side, that's the furthest they can get away. Little tiny molecules are also linear. So something like HCl, HCl. The only one way to draw them is in a straight line. There's only 2 atoms, so we can't draw any other shape. So these will always be linear. Something like H2 is going to be linear. Something like O2 is always going to be linear. Okay, so these are examples of linear atoms. They're pretty easy. They're all 180 as a bond angle. The next two shapes then, you should remember, are trigonal planar and tetrahedral. And again, this is all based off and them being as far apart from each other as possible. So here, BF3 has 120 bond angles. Remember, a full circle is 360. And so in this case, since boron only makes 3 single bonds, it has 1 domain, 2 domain, 3 domain. And so the furthest they can get apart from each other in trigonal planar is 120 degrees, because 120, 240, 360. So trigonal planar has 120 degree bond angle. Tetrahedral is when you have 4 domains. And so it's not, you have to remember this is 3-dimensional. And so you have a central atom, you have one up, you have one sort of coming out towards you, and then you have them coming out the back. And so it looks like this bottom one here. So these bond angles are 109.5. Really, really important to remember. This is 109.5. It doesn't, even though we draw it like this, because we can't draw 3-dimensionally, so it looks like they're 90-degree bond angles, but they're not. Okay? These are 109.5 because it's not flat. This isn't 1-dimensional. It's 3-dimensional. And as a result, you get these big angles that you can see are greater than 90. They're 109.5. That's a really important number to remember. And you'll see why as we go forward. So those are the only numbers you need to know. You need to know linear is 180. You need to know trigonal planar is 120. And you need to know tetrahedral is 109.5. Everything else you're just going to say is less than one of those. And I'll show you an example. So pyramidal. NH3s are really go-to for whenever we talk about pyramidal, right? You have a central atom, you have N, and then you have a lone pair up top. And so remember that lone pair still takes up space. And I guess I should have probably put an N in here. So this lone pair takes up space. And so nothing else is going to be there. And then you have your H's, and they're going to be spread out. And so what this sort of looks like is it's basically tetrahedral because you have one up top, 2, 3, 4. 4 domains. And so whenever you have 4 domains, you're pretty much going to have around a 109.5 bond angle. But what happens is this lone pair, because they're not in a bond, they take up a little bit more space than a bonded pair. And as a result, they push everybody down a little bit more. And so what you end up with is a bond angle. All you have to do is say less than 109.5. The real angle is 107. Don't worry about memorizing it. Okay? So lone pairs will always reduce the bond angle. Okay? Does that make sense? So 4 domains, it's sort of basically based off trigonal planar, but this lone pair pushes everybody down one more. Water is very similar. Water is also sort of based off of trigonal planar. And if we do a Lewis dot, like the old way of doing Lewis dot, where you have oxygen, and oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. And then the H's come in with their 1 electron, making sure we satisfy the octet rule. Oxygen has 8 around it. So again, this is essentially the same thing as this when you do a Lewis dot. Just making sure you're putting your lone pairs. Again, this is based off 1 domain, 2 domain, 3 domain, 4 domain. So it's still based off 4 domains. And so these domains still take up space. And as a result, I don't know what happened there. As a result, they'll still push these 2 bonded pair in a downward direction. So they push these down. And this is bent. And that's why whenever we draw water like this, sort of show that it's in a bent formation. Sorry again for the horrible pictures. Okay. So it has a bent shape, and that's again because of the lone pair electrons that it has there. And so again, you would say that this is less than 109.5. Because again, if these were bonds, it would be tetrahedral, but they're not, they're lone pair. And so sometimes you're gonna hear it said as less than 109.5. Like not a little bit less than 109.5, less than that. Because less than is 107, less than is 104.5. You don't have to say that. All you have to do is say it's less than 109.5. Okay. You're never going to have more than 109.5. It's always less than. Okay. So quick review here. Linear shape, 180-degree bond angle, no lone pairs, and so you end up with these 2 domains. If it has 2 lone pairs up top, then you end up with less than 109.5. If you have 1 lone pair up here, it's less than 109.5. And if it's tetrahedral, it's just 109.5. What if there were no lone pairs on this one? What would its bond angle be if it was 3 single bonds with no lone pairs? I hear mumbles. What was it?
Trigonal planar.
Trigonal planar, and so its bond angle would be what?
120.
Yeah, 120. Okay. So if there were no lone pairs, it just spreads out 120. But again, remember, if it's lone pairs, they get pushed down by this lone pair up top, and that decreases these and doesn't allow them to spread out like this. They can't be 120 when there's a lone pair. And so if there's 1 lone pair, again, just less than 109.5. Okay?
Gotcha.
So then we get into, we'll talk about this later. You should be able to draw Lewis dots and figure out bond angles and shape, but we'll get back to that. Let's try one together. So HCN, what's the total electrons here? C is?
4.
4,
4.
N?
5,
H?
1.
I want to make sure you're always doing this. I saw a lot of people weren't doing it on the homework. You have to count those electrons so you know how many to put. You can't just guess how to make this. Okay? Guessing doesn't work. You need to make sure that you have a total of 8 electrons. And so when we do that, 2, 4, 6, 8, and where does the lone pair go on this?
On
On the end. Good. So 2, 4, 6, 8, 10 total electrons. Again, octet rule must be satisfied for rows 1 and 2. 2, 4, 6, 8, 2, 4, 6, 8. So what shape do we have?
Linear.
Linear. What's our bond angle?
180.
Next one. pH3. P is?
P is 5.
5.
Then we have 3 here.
3.
This is our central atom.
P.
P.
And so we're putting 3 H's around it. So we need a total of 8 electrons. So 2,
Mm-hmm.
4, 6. And am I done?
You have two.
The lone pair on P.
Yeah.
Okay, up top. All right. What shape?
Tetrahedral.
No.
Oh no, never mind. Wait, is it?
Isn't it the triangle one?
Trigonal planar?
Yeah.
Oh, you have a lone pair at the top.
That's. Is that not tetrahedral?
Is it?
Tetrahedral is 4 single bonds.
Yeah.
So would this be less than? I don't remember the.
Wouldn't it be
Would it be
pyramidal? Yeah, the
Pyramidal.
pyramid.
Oh.
And a lot of times you're going to hear it called trigonal pyramidal because it still has 3 bonds. So it's just like trigonal planar, but it has a lone pair. Trigonal planar would mean it has what bond angles?
120?
120. This is
Oh.
trigonal pyramidal, and so it doesn't have 120.
It's either 90 less than.
Less than.
Just saying pyramidal is fine, but you're going to see them use the word trigonal pyramidal. It just means pyramidal. Pyramidal. So what's our bond angle?
90 less than. Oh, no,
So less than.
109.
109.5.
How do I draw the less than sign? So I have 109.5. You don't want to screw it up by making it face the wrong way. So we're essentially saying some imaginary number is going to be what?
Less than.
So do I draw the point facing left or facing right?
Facing left.
Yeah. It's going to be less than 109.5. If you're not comfortable doing this, just literally write the words less than 109.5. This is also fine though. Okay?
Mm-hmm.
Good. Great. Nice job. So then we expand a little bit. You can have more domains than that. You could have, so we've looked at 4 domains. You could have 5 domains. You can have 6 domains. And there's different shapes that are associated with it. So again, if you have 4 domains, if they're all single bonds, it's tetrahedral. If it's 3 single bonds and a lone pair, so if we take off 1 bond, we replace
One domain.
Sorry. So all of these are 4 domains. These are 4 domain molecules. And so that you have these shapes available for 4 domain molecules. If you have 4 single bonds, it's tetrahedral, 109.5. If you replace a single bond with a lone pair, it becomes trigonal pyramidal. And if you replace 2 single bonds with lone pair, it becomes bent. Okay? So we know those. Those are our basic 4 domain shapes. What if we move into 5 domains then? When we get into 5 domains, so if you have all single bonds, we call this bipyramidal. And the reason we call it bipyramidal is if you look at it, it forms sort of a pyramid up top, and try to picture that 3-dimensionally. And then it forms a pyramid on the bottom. And again, you have to sort of picture that 3-dimensionally. So essentially, it has a pyramid up top, and it has a pyramid on the bottom. And this is so much easier when I'm holding up models in classes. In class for you guys, I would never, ever show it like this. But unfortunately, I can't get to school and get the models. So, stuck. I am going to show it to you 3-dimensionally in 1 second. If you replace 1 single bond, you get something called a seesaw. And if you replace 2 single bonds, you get something called T-shape. You'll see this in 1 second. So let's do this. And bring these up. So this is similar to what we were doing in the video yesterday and what you saw. So what shape is this? Stop peeking at that.
Tetrahedral.
4 single bonds, tetrahedral.
Yeah.
What's the bond angle?
109.5.
109.5. If I try to drag these and move them, they'll always go back to 109.5 because that's the maximum distance apart from each other. So if I bend them and try to do this right now, they're always going to go back to 109.5. Again, that's the maximum distance. Okay. Again, I can now remove one of these single bonds and put in a lone pair. What shape is this now?
Trigonal pyramid, whatever it's called.
Pyramidal.
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 So trigonal pyramidal. And what's our bond angle going to be?
Less than
109.5.
1.5.
So
Mm,
I don't know why it's showing it as 109.5. It's not. It's less than 109.5. So ignore that. I can replace another one and put in another lone pair. And what shape is this?
I don't.
Bent.
Bent. Yeah, see, it's just bent.
Oh.
That's just bent shape. And I could then do a third one. And what shape is this?
Linear.
linear.
Linear. And the bond angle is going to be?
180.
And it's not showing bond angle for some reason, but 180. Okay. So now we have 5 domains. Okay. We've added an extra. This isn't tetrahedral anymore. You'll never need to know. Well, I shouldn't say never. I'll go over them anyway. But we see there's 5 domains and that this is a little bit different shape now. And so I want to make sure we can see all 5. This is the one that we call
Trigonal bipyramid.
pyramidal. Trying to get it real vertical here. This is not easy to navigate this thing. Okay. I'm sort of giving up on trying to make this perfect. But so again, you can see it has one pyramid at the top, and then it would have one pyramid at the bottom. That's why it's called bipyramidal. Looking at it, tell me what you think these bond angles are.
90.
90. And what bond angles do you think from here to here is?
120.
180.
180.
So I'm trying to make it a little straighter for you here.
Yeah, 180.
You can see now that it's
180.
linear. So this is 180, and these are all going to be
190.
Okay. So this has 2 bond angles in it. It has 90s, 120s. And so when we have 5 domains, that's bipyramidal. If I remove one of these and I put on a lone pair, now it has a new name. And its new name is called, let's see if I can get it.
Seesaw.
It looks,
How does it?
looks like,
Why is it called seesaw?
I'm trying to get there.
Oh.
It don't even look like one.
So
Yes,
look
it
at
does. Now
There
it
we
does.
go. So
Now
look
it
at it now.
does.
So we have the base of the seesaw, and then you have the straight line here, right?
Mm-hmm.
So if somebody sat on this end, go
That
up,
would
and somebody
go
sat on this end, that would go up. So that's a basic seesaw. That's why it's called seesaw. So you always look for the thing that's just called, looks like a seesaw. What's this? Our bond angles, again, are going to be, we have a bunch of 90s in it. And then that's probably all you would ever need to know for that. These are going to get pushed down a little bit. They're never going to ask you bond angles on these. So the only ones you're really going to need bond angles for are the 4 domain ones. I've never seen them ask this. I mean, could they? Maybe, but I've never seen it asked. And last one, let's remove one more single bond and add another lone pair. And now it is called
T-shaped.
Right.
Yep. Or why can't I make it look like it's E though? Trying. There we go. So now it is T-shape. Why is it called T-shape?
Because it looks like a T.
It looks like a T.
Self-explanatory.
T. So T-shaped. So the easiest way to do these is, again, if I replace these lone pair with single bonds, it goes back to
Bipyramid.
the bipyramidal, right? So really, I can't obviously show you with my hands right now, but cover one up, right? So it loses one bond. So it has 4 single and 1 lone pair. So we cover this with our hand. What shape do we see? Let's go, let's do it this way.
The seesaw?
Yeah, we see the seesaw, right? You should be able to see the seesaw if we cover it with our hand. If we cover this top one with our hand, we have seesaw. And then if we cover another one with our hand, we end up with T-shape.
T-shape.
Right? If I cover this one and I cover this one, then I'm left with T-shape. That's it. That's all you need to know.
Okay.
Yes. Okay.
Mm-hmm.
End that share, and we'll go back to our PowerPoint again. And so if you could do that, you're in great shape. Then there's this thing that's called hybridization that probably sounded really confusing on the video. It's
Mm-hmm.
the easiest thing ever. Okay? Here's what you do. You look at domains. How many domains are here?
2.
The first one's called S. The second one's called P. So we say this is, the hybridization for this is S-P hybridization. The first one is always called S. Everyone after that is called P.
Mm-hmm.
So this is, and it doesn't matter which one you start with. If this is S, this is P, this would be another P. And so if we have an S, a P, and a P, we would say we have SP2. Down here, the first one's always an S, then a P, and a P. How many P's is that?
3.
So we call that SP.
3 hybridization.
That's it. That's hybridization. They made it sound really confusing. It shouldn't be. And so here we have tetrahedral again. What is the hybridization for tetrahedral? Well, it's going to be S, P,
P3.
P, and P. So SP.
3.
So tetrahedral is always going to have sp3 hybridization. We use these words sigma and pi bonds, and this is also extremely simple. Sigma bonds are always the first bond you ever draw. Any other bond you add is called a pi bond. For example, if we look at this molecule, C with a triple bond between it. The first bond is always sigma. Everyone after that is a pi bond. So this has 1 sigma and 2 pi. If we were doing CO2, what type of bonds would we have here? The first one is a
Sigma.
second one is a
Pi.
over here. First one is a
Sigma.
Sigma.
second one is a
Pi.
pi. That's all sigma pi bonds are.
Oh.
Okay? So this hybridization, the sigma pi bond, it's really, really easy stuff. You just have to try to remember it. And so that's all you have to do with those. So if I did, so let's do, what would these be?
Sigma, SP.
Sigma, yep.
Mhm.
So this is sigma, and over here is
Sigma.
Sigma.
What is the hybridization around this carbon right here? So first, let's go through everything. What's the shape of this molecule?
Linear.
Linear. What's the bond angle? So
180.
we're only gonna, again, we'll only focus on the carbon. 180. What's the hybridization around this? So it has this domain and it has that domain. So the hybridization is
SP3.
SP. SP.
first domain is
S.
and a triple bond counts as one domain. So it is
Oh, SP.
SP. If it said label the bonds, we would say this is sigma, sigma,
Sigma.
pi, pi. The symbol for sigma is this. And pi, you already know is.
Pi.
So if it said label them, so let's see. I have this. I'll do CH2. Oh. If I said label the bonds, so what would I label this one as?
Sigma.
Sigma. So I can put a little sigma. This would be,
Sigma.
doesn't matter which one you pick first, as long as one of them is a,
Sigma.
Sigma pi.
and one of them is a. What is the hybridization around this molecule? One domain, two domain,
Three.
three domains. So it is.
Two.
S.
S is the first one. And then we
Is it-
have,
SP cubed.
SP2.
Yes.
what's the bond angle associated with sp2?
Oh, shit.
What is that? 120?
Perfect. 120 bond angle. What's the shape?
Trigonal planar.
Trigonal planar.
Wait, so why wouldn't it be SP cubed?
Why would it what?
Why wouldn't it be 3 instead of 2?
Because you count the domains. So I know it's sort of mucked up here a little bit. That was with an M. Mucked up. Don't want to have to. So this is one domain. This is the second domain. And this is the third domain. There's no lone pair because this carbon has 1, 2, 3, 4 bonds. So the first one is S. And then the second domain is a P. And then this third domain, you have another P. So it's SP.
So if it was 4 domains, it would be SP3.
Yep.
Okay.
Domains
All
is
right.
always SP3. So methane, CH4. Going to be one domain S, P, SP2, SP3. Okay. So if it's label the sigma pi bonds and give hybridization, so really easy here. What are we putting on it?
This is sigma.
No.
Pi. Sigma. It's linear.
Linear,
So it's SP hybridization.
SP hybridization, good. Because it has one domain. You always do it around only your central atom. Don't be confused. Don't go out here and look at the O and go, oh, it has 1, 2, 3. The O has a different hybridization. They're only ever going to ask you for the central atom. That's all we ever care about. Because that's really what the whole molecule shape is based off of, is that central atom. Strength. So a single bond is always going to be sigma, right? That's always going to be sigma. So anytime you have a single bond, it's the first one, it's always sigma. So sigma bonds, if I have a C and an O here, and they're single bonded, because maybe there's something else over here, whatever. So only looking at this, if that's a single bond, it's going to be longer and it's going to be weaker than a double bond, than if we had a pi bond. Because if we had another pair of electrons, they get pulled tighter. So they're now stronger. The more bonds you add, the stronger it gets. So if you had a pi bond is going to make this stronger than just a single bond. And obviously we wouldn't have a double and a single here. It's a crappy example. But a double bond is stronger and shorter than a single bond. Make a prediction about a triple bond.
It's gonna be stronger than a double bond. And stronger.
Stronger, and what about the length?
Shorter. Would it be shorter, right?
Yep, shorter and stronger. The more bonds you add, the tighter everything gets pulled together because they get pulled close to the nucleus. And our last two slides. So here's, ignore all the red. All this is 2 carbon with a single bond, 2 carbon with a double bond, 2 carbon with a triple bond. Here is their bond length that they were able to measure of those bonds. In ethane, which is this one, this is the first one, the bond length is 153 picometers. We don't care about that. We just know that this is a bigger number than those. So a single bond is longer. Then the double bond's length is 133 picometers. And then the triple bond's length is 120 picometers. So this is just showing you that the bond length gets shorter as you add more bonds. Which bond is the strongest? Ethane, ethene, or ethyne?
Ethine.
Ethine. Triple bond's going to be the strongest. So let's do one complete problem together. Starting from scratch. NO2 minus 1. How many valence electrons? N has?
And as 5.
O
As times
and 2 of them, so that's
12.
plus 1.
and the minus means it gained.
Elect
Now that is
1.
total is
18 electrons.
so drawing it
And
and
Oh.
so if I do this 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Is that correct to have 2 single bonds?
You can.
I need 20 electrons to make everybody stable. So I need 18. So when you have too many electrons, then you make
a double.
double bond. And did it matter what side I put it on?
No.
It doesn't. So
No.
I'm going to put it here, and I'll put my lone pairs. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 8. So let's count our total electrons. Do we have 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. Is this an acceptable Lewis structure for NO2 minus?
Yeah. The bracket and the mic. You don't have to do them.
Good.
Yeah.
We need the bracket with the minus. Because do I only have to draw this one way?
No.
No, I have to draw it both ways. Because
I have to do it both ways.
That's
it's
no
not just on
bueno.
the left, it's also on the.
Right.
What do we call this when we draw 2 versions like this?
Resonance.
Resonance.
Yeah.
Good. These are resonance structures. And so we go through and we put all our electrons on.
Structure gang.
And just because, what is the formal charges on the, let's do it on the right one. What's the formal charge on this O? How many should oxygen have?
6, it has 7.
That's 6 because it's in family 6A, right?
Yeah.
It has 2, 4, 6, and we only
Seven.
count,
One of
when we're doing formal charge, we only count one, right? For the octet rule, this is 2, 4, 6, 8. But when we do formal charge, we only say one of these goes to the collect charge. So this is 6 minus 2, 4, 6, 7. So the O has a
-1.
Negative 1.
-1. What about the N? N should have,
5.
it has
1,
2,
2,
3, 4,
Four.
5.
5,
So this is a,
there's a 0.
and over here,
Should have
2, 4, 6.
6.
2, 4, 5, 6,
Yeah.
6, 0.
0. Does our overall formal charge match the charge of the molecule?
Yeah.
Yeah.
Yeah, -1, -1. Good. So those are two resonance structures. There's the formal charge, real basic stuff. So I'm going to change this word. I don't like this word groups. I like domains. I don't want to use some crappy fake word. So how many domains surround the central nitrogen here?
1,
1,
2,
2.
3.
3. Do we all agree with that?
Yeah.
Again, 1, 2,
2,
3. So there are
3.
domain.
As a result, what is the molecular geometry of this one? So again, we're looking at it. We have N, we have a double bond, O. We have a single bond, O. And then we have a lone pair here. This is a hard one. What's the geometry of this?
Hmm. Isn't it? It's not trigonoplanar. Is it bent? I don't know.
Yeah, I would say this is bent.
Mm-hmm.
Yeah.
It's going to be bent. And then we have this lone pair bending it down. What is the bond angle going to be? So again, how many domains does it have?
Now 3.
2.
3.
It has 3 domains, right? The central N has 3 domains. And 3 domains normally is what shape?
The
Trigonal planar.
Normally trigonal planar. And what's the bond angle for trigonal planar?
120.
120.
120. So this is going to be a bond angle less than
1.
120.
Mhm.
This is a hard one.
Wait, why?
Because it would normally be, if this was a single bond,
Would be trigonoplanar.
it would be 120 apart, right?
Yeah.
So 120, 120, 120. But it's not a single bond. It's a lone pair. And so instead of being 120, it gets pushed a little bit shorter, a little bit in, a little bit more. And that makes it less than 120.
Okay.
Okay? So you always have to remember, if this were a single bond, what would the bond angle be? Okay? And that would make it then less than 120. Looking at only at the atoms, again, this lone pair pushes these down and it makes it bent. Don't get, you know what? I shouldn't have.
Shape and
This is a little bit confusing. So what they meant, the overall geometry is trigonal planar because there's 3 domains, but the shape is bent. Okay?
Oh,
They're never going to ask you both. Don't worry. Just say bent. That's enough always. So what's the bond angle? We already said less than.
less than 120.
Less than 120. And is this a polar molecule or not? So N and O have differences in electronegativities. I forget what they are offhand. I don't have an electronegativity chart, but I believe it's polar.
Yeah, because of the O.
Is the overall molecule, do these cancel out?
No.
No, they're not equal and opposite. So
Yeah,
it's a
go.
polar molecule with polar bonds. Good, so that's an awful lot of stuff I just gave you guys, but you guys did a great job with that. We're in the last week of the term, and we're down to really one chapter. So we should be finished. We lose a week with April break. I'm going to stop the recording real quick.